Welcome to The Explainer. Today, we're jumping right in to demystify the absolute magic of modern automation. We're going to do this by tracking a single, seemingly simple, movement command. We'll follow it from its birth as digital code all the way to its execution as physical, surgical motion in the real world. If you've ever watched a robotic arm in a factory seamlessly assemble a car or place a microscopic chip on a board, you are literally watching a mathematical symphony. So let's dive into this and see how that symphony is actually composed.
But first, let's shatter a pretty common illusion. When we watch a robotic arm reach out and grab something, it's supernatural to project our own human qualities onto it, right? We just assume the robot kind of looks at its environment, sees the part, and reaches out to grab it, exactly the way you or I would reach for our morning coffee. But the reality? It's far more fascinating. Robots absolutely do not look at their environment the way we do. Fundamentally speaking, the robot is blind.
So if the machine is completely blind, how on earth does it know where to go? Well, it operates purely on coordinates. The software actually has to run incredibly complex calculations just to get the tip of the arm to a specific point in space. It receives an X, Y, and Z coordinate, let's say the exact location of a screw on a circuit board. From there, it relies heavily on trigonometry. I'm talking about calculating the precise rotation for every single joint, the waist, the shoulder, the elbow, and the wrist. It's essentially a massive mapping problem, translating a location in our physical 3D space into a set of angles that the robot's motors can actually understand.
All right, Section 1, How Blind Robots Reach.
To really wrap our heads around this, we have to begin the journey of our command by defining the destination and the physical limits of the robot itself. Before any of that trigonometry can happen, we have to know what we're moving and where it's allowed to go. Which brings us to a crucial term, the end effector. This is the tool, the gripper, the welder, or maybe the paint sprayer located at the very tip of the robotic arm. The main takeaway here is this: every single calculation the software performs, every line of code, every ounce of electrical power is strictly in service of getting this specific part, the end effector, to the target destination. The rest of the arm? That's really just the delivery mechanism.
And we have to map out exactly where that delivery mechanism can physically operate. We call this the workspace envelope. Depending on how the robot is designed, it has a specific 3D dome of physical reach. What's absolutely vital to note here is that our mathematical commands must respect physical reality. The math might say, hey, a negative radial value is a perfectly valid solution to this equation. But physically, the arm might only be able to bend forward. If the coordinate falls outside this 3D envelope, or requires a physically impossible joint angle, well, the command fails before it even starts.
Moving on to Section 2, the math of movement.
With our physical limits totally locked in, our command now enters the mathematical gauntlet. This is where the heavy lifting really happens, translating a destination into a blueprint for movement. Enter Inverse Kinematics, or IK. Think of IK as the ultimate translator. Forward kinematics is relatively easy. If I tell you the angle of every joint, you can easily calculate where the end effector will end up. But inverse kinematics goes the opposite way, and it is vastly more difficult. It takes a human-readable 3D coordinate in Cartesian space and works backward to calculate the complex set of robot-readable joint rotations needed to get there. It's often a one-to-many mapping, meaning there might be a bunch of different ways the arm could contort itself to reach the exact same spot.
We can clearly visualize that translation when we look at the underlying geometry. Euclidean distances are literally being translated into specific joint angles. The system is heavily relying on the law of cosines and the law of sines. It essentially draws a theoretical triangle between the base of the robot, the elbow joint, and the target coordinate. Because the software knows the fixed physical lengths of the arm segments, it can calculate the exact angles required for the motors to hit that target.
But of course, industrial robots aren't just flat two-dimensional lines on a chalkboard. They have multiple degrees of freedom, or DOF. This is the number of independent axes the robot can move. A standard industrial arm typically has 6 degrees of freedom, which allows it to reach a point and orient the end effector in literally any direction: pitch, yaw, and roll. The software has to solve those dense trigonometry equations for every single degree of freedom simultaneously, in real time. Oh, and some advanced robots are what we call redundant, meaning they have 7 degrees of freedom. That extra joint gives the robot multiple ways to reach the exact same point, which is a total game changer for reaching around physical obstacles in a cluttered workspace.
Which brings us to Section 3, the singularity trap.
Right in the middle of these intense calculations, our command faces a high-stakes mathematical hazard that engineers have to very carefully program around. We really have to contrast a normal, safe operating position with what's known as a singularity. In a normal position, the math is totally predictable and the movement is smooth. But a singularity, that's a dangerous mathematical trap. It happens when two or more of the robot's joints align in a perfectly straight line. When this alignment occurs, those inverse kinematics equations we just talked about suddenly hit a brick wall. They effectively try to divide by zero. The math just completely breaks down, suggesting there are an infinite number of solutions. To physically correct itself or maintain its path through a singularity, the robot's joints would theoretically have to spin at an infinite speed. Obviously, no real-world motor can do that, and trying would severely damage the machine.
And honestly, this is where the brilliance of modern robot controllers really shines. The system is constantly, actively monitoring the robot's constraints. If the controller detects that the arm is approaching one of these mathematical traps, it doesn't just crash or freak out. It automatically injects microscopic perturbations, just these tiny, calculated joint angle increments, to essentially nudge the arm slightly off its perfect trajectory. It's an elegant little sidestep. This allows the robot to safely bypass the singularity and continue its movement smoothly without the math breaking down.
All right, Section 4, Taming the Dumb Motors.
So, our coordinate command has safely navigated the mathematical singularities and the inverse kinematics. Fantastic. But math alone doesn't move metal. The calculated angles must now be transformed into physical electrical voltage. And this brings us to a massive contrast in robotics. Electric motors at their core are inherently dumb. If you give them power, they just want to spin wildly until that power is cut. They have absolutely no idea when to slow down. That is exactly where PID control comes in. The proportional integral derivative controller is the crucial intelligence that feathers the brakes. It's a continuous feedback loop that is constantly comparing where the arm currently is against where the inverse kinematics says it should be.
Let's break down how this builds step by step to narrow that positional error down to exactly zero. First, the proportional, or P term, reacts to the current error. Basically, the further away the arm is from the target, the harder it pushes the motor. But P alone usually leaves a tiny gap, a steady state error. That's where the integral, or I term, steps up. It accumulates past errors over time, gently nudging the arm to close that final stubborn gap. Finally, the derivative, or D term, acts as a shock absorber. It looks at the rate of change, the trend of the error, and kind of predicts the future. If the arm is coming in way too hot, the D term dampens the response so the arm doesn't oscillate or overshoot the mark. Together, they create this absolutely perfect, smooth stop.
And finally, Section 5, the heart of precision.
This is where we get to watch the synthesis of brilliant mathematics and highly controlled electrical power stop a massive metal arm on an absolute dime. It really is an epic journey when you think about it. It started as a blind, human-readable coordinate in a 3D workspace. It survived the rigorous trigonometric translations of inverse kinematics, getting mapped from Cartesian space into joint space. It safely navigated the dangerous mathematical cliffs of singularities thanks to intelligent constraints. And finally, it was executed flawlessly by the PID controller, which feathered the voltages to the motors, bringing the end effector to the exact pose required with sub-millimeter accuracy. It's just a real-time miracle of engineering.
Now, for those of you focused learners who really want to dig into the heavy math, the control systems, and the real-time operating architectures we've talked about today, these are excellent jumping-off points. Diving into industry and academic literature on robot kinematics and dynamics, like FANUC or ABB motion planning white papers, the IEEE Robotics Library, or John Craig's foundational Introduction to Robotics, will give you a lifetime of fascinating material on exactly how we command machines to manipulate the physical world.
And that leaves us with a pretty compelling thought to chew on. We've seen how rigid math and classical PID control can force blind, dumb machines to move with incredible surgical precision. But as we look to the horizon, what happens when we start replacing or augmenting those rigid geometric equations with predictive AI? What happens when the feedback loops don't just react to error but actually learn and anticipate physical interactions in real time? The journey of a command is only going to get faster, smoother, and vastly more intelligent. Thank you so much for joining me on this explainer. I hope this sparked your curiosity to learn even more. See you next time.